behalf of Engineers Australia, I'm delighted to welcome you to tonight's event discussing weatherability of topcoats. My name is Susie Waterston. I'm the Stakeholder Engagement Manager for Engineers Australia and I'll be your host this evening. So firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians throughout Australia and recognises their continuing connection to land, waters and skies. We pay our respects to them, their cultures past and present, and today we present from the Whadjuk Noongar country, the land of the Noongar people. I just thought I'd highlight, we've got a really beautiful painting as you enter the BLE auditorium. The reason this auditorium is named that is because of this beautiful artist. Her name is Fiona Reedy. She painted that piece out there that you see, titled Raindrops on the Belia. It looks at the flow of water through the different Noongar seasons, and as we're based alongside the beautiful Dribble Yerrigan, the Swan River, the flow of knowledge goes in and out through the Belia depending on the Noongar season. And we believe that the flow of knowledge goes in and out of this auditorium that you're sitting in today. So very, very relevant to engineers. So before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Dulux Protective Coatings. As one of the leading manufacturers and suppliers of protective coatings, within Australia proudly protecting Australia and New Zealand's assets for over 90 years. Their comprehensive range of protective coatings helps protects, maintains and enhances assets and infrastructure across diverse industries, including bridges, water and wastewater, rail and road transport, public facilities, commercial building, mining and a wide range of heavy industrial settings. Products are tested specifically for Australian and New Zealand conditions with the capacity to manufacture locally coupled with extensive network over 230 stores. Their experienced and trained technical consultants have the means to ensure the right coatings are supplied for your specific project on time and with confidence. Today we'll hear from two guest speakers, followed by audience Q&A, and I encourage you to send questions through to our speakers via the chat box for those online audience, and there'll be an opportunity in person with a roving mic for you to ask your own questions. We have guests joining online and we welcome you all, so please make sure you utilise this Q&A function. So firstly, I'd like to welcome our first speaker tonight, Rob Kildare, Technical Executive for Minerals Performance at WSP. Rob is one of Australasia's leading practitioners in asset durability and materials performance. He has an international reputation for solving materials-related challenges and providing pragmatic advice related to materials selection, durability, constructability and long-term asset performance. 25 years of global experience leading infrastructure project delivery across Australasia, the Middle East and the UK. He has contributed to the success of various mega projects, Burj Khalifa, thank you for that correction. Perth's Metronet, which I'm a lot more familiar with, thank you, the program, and has delivered a diverse portfolio of asset condition assessment and remediation projects across water, energy, transport infrastructure and building sectors. Please welcome Rob Kildare to the stage.
Can you hear? Yeah, there we go. Awesome. All right. Design for life. And this is about one of the Metronet projects that we've been working on for the past couple of years. So to kick things off this evening, I'll present a case study from one of the major rail infrastructure projects here in Perth. Currently in its final stages of construction, it has used advanced UV-resistant protective coatings. So I'll provide a brief project overview, and then I'll try and highlight some of the key constraints that we had to deal with in terms of selecting the coating and why we ended up with the solution we did. And then I'll provide a bit of background on the science and summarise with some final thoughts around how we should approach sustainable design solutions. So the project, and it's not the nightly TV show. Part of the Metronet project is the Armadale Line level crossing removal. You can see that here on the screen. This is part of an 8-kilometre viaduct that runs between Carlisle in the east and Beckenham in the southeast of Perth. As with other major rail infrastructure projects being delivered as part of the Metronet program, the primary structural steel elements are required to achieve a design life of 120 years. And the design life in this particular case is defined as the time to first major maintenance. So it's a pretty substantial period of time to try and rely on a protective coating or the structural steel in itself. With this specification, the asset owner has signalled to the market a desire to achieve extended asset operations without major maintenance. And the primary reason is that in a commuter rail environment, uptime and operations is critical. Shutdowns can be both very costly and very disruptive. So to achieve the very long design lives on Metronet projects, galvanising of the steel remains a primary method for providing robust corrosion protection systems that require minimal maintenance, and it's part of the client's standard specification. And there's some reasonably robust technical reasons for this. We can predict with reasonable accuracy the likely deterioration rate of galvanising under certain exposure conditions. We know it's not impacted by UV exposure, and we know that it can take some hard knocks when it's been installed on site, which can be a benefit, enabling low maintenance structural applications. However, for this particular project, there were some configurations for some of the building elements that led us to explore a different solution because they had the potential to add significant cost and complexity if we were to continue to galvanise them. So with some elements also requiring painting after galvanising, it became apparent that there was really a significant need to try and step back and explore some alternatives. This was a system challenge that the team had to address. But first, this is the project alignment and the exposure environment. It's largely dominated by wetting and drying cycles and the accumulation of dust and low amounts of airborne salts, equivalent to what we would class, according to the Australian and ISO standards, as a C2 exposure. Select elements that are not exposed to rain washing are probably exposed to an equivalent C3 exposure class, but it's perhaps less relevant for the elements that we're discussing this evening. Some of the elements are architecturally expressed structural steel, and those elements are the ones that we paint. Some elements are also exposed to high traffic environments requiring high levels of robustness, but also aesthetic appeal. And in this particular case, it was the lift shafts that fell into that category. So the majority of the structural steel is behind cladding. And we could show that galvanising would be fine to satisfy the 100-year life to first maintenance. But as I mentioned, the complexity of galvanising was going to add increased cost and was a driver for exploring alternative corrosion protection systems. The initial query was raised during early procurement when these large lift shafts, which are shown in green, were put out to the market for pricing. We identified that there was a potential for a 40% premium on a standard welded solution, which the designers had originally proposed, to enable a galvanised and painted solution, because we would have to introduce a whole lot of flanges, whole lots of bolts, because of the size and of the welded steel frames, which were more than 25 metres high and more than 3 metres in width. Too large to fit into the available galvanising baths here in Perth in Western Australia. So while the capital cost premium was a driver, the design team was also mindful of the laser focus that the client has on durability and maintainability of their assets within the rail corridor. And an alternative solution had to provide an extended time to first maintenance, particularly where there was limited access for doing maintenance in the future. So some of the questions we asked ourselves were, could we meet this long life performance requirement? And what would be the impact on cost? So some of the client concerns, we'd have to allow for extended periods between maintenance cycles. So we might not necessarily be able to meet 120 years, but we were unlikely to get a protective coating system that wasn't galvanising across the line if we couldn't show that we had a system that could potentially reduce the number of interventions over the asset's life cycle. And the current code provides kind of limited guidance in terms of the ability of coatings to survive for longer than 25 years. And you'll often find that provides a little bit of anxiety around specifying protective coating systems for very long life applications, because the majority of applications in the code are either less than 30 years, have less than 30 years track record in the Australian market, or have been shown to actually not perform that well under harsh UV conditions that we experience here in Australia. Organic coatings can also be a little bit less resistant to the bumps and knocks that you might get on site during construction, leading to ultimate serviceability impacts if repairs aren't implemented correctly. So we come to the topic of the evening, top coat weatherability. And when it comes to protection of the coating, when it comes to protective coating system life, there's a number of factors that can influence this. The exposure environment, which I've presented, the surface preparation, and the application of the coating are all critical. And the paint system specified is largely influenced by these factors, but also the client's requirements in terms of maintainability and aesthetics, but also the total cost of ownership. And a typical three-coat paint system, the hard work in terms of corrosion protection is done by the primer and the intermediate. But it is that top coat that provides that first line of defence for the coating system. And any degradation of that top coat can lead to changes in appearance, film erosion, and ultimately failure of the coating system. The Australian standards present various long life coating systems, including polyurethanes and polysiloxanes. And they're typically expected to provide at least a 25-year service life to first maintenance, according to the codes. And while it's possible to extend these service lives for maybe up to 40 years or more, this is very much dependent on the film thickness, the exposure, and there's been a lot of testing that shows that some of these systems can be failing in as little as 15 years under very aggressive conditions. So on the project, really, weatherability and ability to resist UV were the critical factors for the coating that we selected. And that solution is a 3-coat paint system based on fluoropolymer. Fluoropolymer is a resin that was developed in Japan over 35, well, in the early 80s for infrastructure and marine structures. And it has demonstrated performance of over 35 years with regards to UV resistance and resistance to very hot and humid tropical environments. And when compared to a typical polyurethane, the fluoropolymer has showed marked reductions in film erosion, particularly when exposed to high UV radiation, and also salt spray consistent with a tropical island exposure, with average degradation rates suggesting we could get a film service life of at least 100 years from just 25 microns of coating, in theory. In practice, we'll go through that. So the science, and Michael will provide a whole lot more detail on some of this in his presentation, but it was my curiosity that drove me to ask, okay, what is the reason behind why these fluoropolymers perform so much better than other coatings? Because I needed to be confident that the solution I was putting forward to our client was going to meet their requirements. So I did a little bit of digging and found that these coatings are really resistant to UV degradation because of the fundamental chemistry of the fluoroethylene vinyl ether, which forms the backbone of the resin in a fluoropolymer coating. And it turns out that the bond energy of the fluoroethylene significantly exceeds that of the energy of the incoming UV light, and because of the concentration of the resin within the coating, it demonstrates superior UV resistance. And so on this particular project, conservatively, we estimated that we could get at least 60 years to first maintenance from the fluoropolymer top coat, which provided us some confidence that we could put the system forward as an alternative to the galvanised and painted solution. But of course, there's a cost impact, and we weren't sure what that was to start. Would it be cost effective over the lifetime? And how would it impact the total cost of ownership for the client? And so we did some more digging and identified that we completed an assessment of the likely cost for acquisition, inspection and maintenance of the asset lifecycle using an economic lens, and combined that economic analysis with both pragmatic experience and industry data on the performance of this fluoropolymer coating. So with an assumed lifetime to first maintenance of 60 years for the fluoropolymer system, and in this particular chart we've called it PUR5FP to distinguish it from the traditional, the polyurethane-based PUR5 system defined in the Australian Code. We found that the service life between maintenance intervals would be at least twice that of a comparable polyurethane-based coating system. The cost data indicated that there would be an initial capital cost premium of around 10% to apply that coating compared to a PUR5 system. However, once we compared the number of coats that you would need to do over a 120-year life, we estimated you might need 3 for a PUR5, where you could possibly get away with potentially one recoat for a PUR5 FP or fluoropolymer-based system. And our life cycle analysis indicated that ultimately the fluoropolymer-based coating system would result in a life cycle cost of about 60% of the comparable solution using galvanised plus painting. And this is schematically what it would look like. Not a lot different from your average 3-coat paint system, where you would have a really good surface preparation, a zinc-rich prime coat, a barrier coat pigmented with micaceous iron oxide to provide that longevity, and then a fluoropolymer top coat. And we have found that in practice, this fluoropolymer top coat it appears to be a lot tougher than the polyurethane, a lot more impact resistant, and it presents itself with a very glossy and slippery surface, which is advantageous in terms of preventing dust and dirt accumulation, which then enhances the durability of the paint film. And so this is one of the lift shafts that was fabricated for the Carlisle station. This is in the workshop, and it does look reasonably complex, but imagine that with a whole lot of extra flanges and bolts, and it becomes apparent that the painted solution was a lot more elegant, and it certainly provided a lot less. Well, it was a lot cheaper, capital cost-wise, but also we demonstrated a lot cheaper over the life of the asset. And this is the Carlisle station in the early stages of construction. So the lift shafts are where the red arrows are on the slide there, and the architectural exposed steel is are the elements on the extreme right and left of the image. And as that project has progressed, because of the architects really liked it, so they made sure that they requested that it was applied to a lot more of the architecturally exposed structural steel than was originally intended. I guess this brings me to my final sort of remarks around systems thinking. I found it was really important to, I guess, highlight the fact that a bit of curiosity and systems thinking can help steer us in the direction of some of these solutions and influence good design. And as designers, our materials selection decisions can significantly impact the cost to implement our designs, as well as how long they will last, how much they'll cost to maintain, as well as their ability to actually deliver the form and function required by our clients. Simple configuration changes can have a really large impact, considering the broader context in which the design will exist, and it's vital to identify solutions that will enable long life, particularly when we're defining systems for corrosion protection, where we're spending large sums of money to create assets that will serve the community. And it's always good to also remember that what's worked elsewhere in the past may not necessarily be appropriate for what we're designing now or into the future. And not all prescriptive requirements will be appropriate for every situation. But if we start with an outcome in mind, we can explore the possibilities. So this project has shown that we need to be mindful of efficient design, and that there's many ways to achieve durable, low-maintenance assets. A healthy dose of curiosity, systems thinking, and ability to explore can help us resolve some of the system challenges. And this project has really provided that opportunity to step back, explore the broader system, and identify a solution that can potentially achieve a design life to first maintenance, who knows, maybe 100 years, using the enhanced weatherability of fluoropolymers. Thank you.
Thank you, Rob. Our next speaker, Michael Filmer, is a professional with over 3 decades of experience in the paint and coating manufacturing industry. He began his career working closely with trade market and applicators and later shifted into the industrial specialty, contract manufacturing sectors for protective coatings. In his current role, Michael is responsible for preparing and documenting specifications for new and maintenance projects. His expertise enables architects and designers select the most desirable, visually appealing and suitable protective coating systems for their clients and their assets. With extensive knowledge and attention to detail, Michael ensures that customers receive the best possible coatings for their needs. Without further ado, please welcome Michael to the stage.
Good evening, everybody. Great presentation, Rob. That was excellent. Hopefully I can elaborate a little bit on that for you as I move through my presentation. I know it's difficult for you getting here tonight also, so thanks for your patience in getting here, and hello to all our online people as well. So as I said, hopefully I can give you a bit more insight as to the choice of the fluoropolymer being chosen for the MetroNet Armidale level crossing removal program, but we'll also go through other coating systems as well, which are commonly used throughout the industry and also on major infrastructure projects. It was interesting that Rob mentioned, 120 years design life was required, for first paint or durability or maintenance. Commonly see 100 years is generally a target with maintenance programs throughout that 100 years. The Australian standard 2312 is a durability standard, so it really only provides you corrosion durability. And unfortunately, at the moment, I don't think there's really any guide for colour stability in the Australian standard, which would be quite difficult to do as well. But you may have high-end durability, but a lot of the time, infrastructure, especially with asset owners, it's the appearance of, or the aesthetic of the coating of the steel that generally requires or engages, new repaints on a lot of infrastructure projects. Just, what is paint? A lot of you may know this. This will vary from manufacturer to manufacturer, but for the products that we use, generally the binder resin system makes up 50-60% of the coating. That can be, diluted with solvent, again with 20 to 40%, and then obviously pigment for colour around 20 to 40%, and also including additives that might give, extra aesthetics or provide extra application features and benefits as well to those. And that component of paint is, for single pack component coatings generally also, and also for 2-pack component coatings also. Colour degradation, 2 things normally. Normally the binder resin can break down, or also the pigment or the colour can break down. Once that happens, once they're impacted, the sheen of the finish, again, the aesthetic appearance takes a real nosedive, and generally that's what engages people to recoat. There are many options available to coat or protect an asset, different types and brands and marketed and put forward on projects. specifies engineers like yourselves will choose the best system that suits the requirements of the project. Obviously, there's a big cost factor in that also. Understanding limitations in application and moving large amounts of steel or substrate around from projects to projects will have a big bearing on what can be achieved and what can't be achieved. Comparing coatings, it's when we manufacture coatings, it's generally not practical for us to wait around, manufacture a coating, paint it, and do some real-world extensive testing for colour durability, coating performance or corrosion performance. So a lot of the time we do accelerated weathering testing. So in the next few slides, I'll be going through some of the accelerated testing that we've done with various top coats out there in the market. But what we do is try and marry up and hopefully find some correlations between real-world testing and obviously weather accelerated testing as well. So really the accelerated testing just bolsters what we know in the field a lot of the time. So the techniques or the tests that were undertaken, third-party testing I'll add to, two tests, the QUVB, which really is a fairly harsh test, and it really gets down and tests the impact that the resin will have over the testing process. And the Xenon Arc, or the QSUN I'll refer to in this test, is more simulates a day-night scenario or real-world conditions as well, and then we'll sort of pick up on pigment performance from that as well. So the QUV testing, the regime for that was, so there were 4,000 hours each. I'll get to that in a minute, but the testing was, the QUVB was 4 hours condensation at 50 degrees. So 4 hours of light, QUVB light, and then 4 hours of condensation at 50 degrees. The QSUN was a cycle of 3 hours light at 63 degrees and 1 hour dark water spray at 25 degrees. So constant testing there. And obviously, every colour will perform differently. You probably notice that when you even paint around your house, inside and outside, or if you're like me, you look at paint systems wherever you go, and you look at faded systems and corrosion and that type of thing. But the three colours we chose for the testing were quite common colours, as well as quite bold colours as well, where there's a lot of pigment used as well to get a real clarity of test, and an even test spread on different types of colour pigments. So Australian Standard 2700 B22 Homebush Blue, Colorbond Monument, which we may all have around our homes as well a little bit, and Australian Standard 2700 R13 Sigma Red, which is used for a lot of identification, marking, safety, and in industry as well. We did 5 commercially available top coats were selected in the test. They were, like I said, coatings that are commonly used within the industry, and I'm sure you've been front and centre with them a lot of the time with a lot of coatings. The polyurethane, and Rob touched on these as well. The polyurethane, commonly used, it's been around for some time in Australia and globally. You'll see it in a lot of different areas, structural steel, you'll see it on concrete, pylons, bridge abutments, that type of thing for protection. You'll even see it on your vehicles and some flooring aspects. The fluoropolymer, a relatively new technology, especially in Australia, but you'll also see it's that same technology that's used in powder coating. So if you ever see powder coating and you think that's lasted quite some time, like even your Colorbond roofs, generally you find that's a fluoropolymer resin system. Polysiloxane provides very good abrasion resistance and very good cleaning ability with those, and you can apply high builds with that particular type of technology coatings, and that can sometimes limit what might be a 3-coat system to a 2-coat system. So it's all about, again, getting back to practices about achieving results depending on the type of project. Polyaspartic, relatively new, but it is out there globally and in Australia and New Zealand. You probably also come across it nowadays in a lot of flooring coatings as well. You'll probably see it. So they use that for quick processing and quick return to service type environments. So the testing rigour for both tests, intervals of 250 hours, and from that they were able to take measurements of gloss and colour of the test panel and compare those with initial value of what the starting point was. Photographic records were taken. Although the testing process was long, 6 months, it still far outweighed, sometimes the 10, 20 years where companies like ourselves have got panels out there in the field within their laboratory sort of departments and evaluating them every 6, 12 months. But the images show in the testing I'm about to show with some of the pictures is variations in change in colour and gloss you'll find. Might be hard to pick up the gloss changes, but you'll be able to see the colour changes. So these photos were also presented by Rob, but so you got the fluoropolymer after 1500 hours. It's still, with the QUVB testing, it's still looking relatively new, you could say. Polyaspartic at the end, starting to show some signs of, some colour chalking. The other, the PURA, the polyurethane A and the polysiloxane, no real dramatic effect, like not something you'd probably pick up with your eye, but if you're comparing it back to the starting point, then you would find some change. But after 3,000 hours, you really start to see some changes there. With the PSL, I'm not too sure that was a damage during, I'm not too sure why it was damaged during the testing. I'm not too sure what's happened there at the top there, but you see the polyaspartic and the urethanes are really starting to lose their colour after 3,000 hours in this test. But remember, this is a really harsh test as well, but it's really digging down on the resin system of this test. Just how to interpret it. So during the test, the equipment that puts the UV light onto the samples, it's only done in the last 2/3 of those panels. So the top third of those panels is the what you use as the standard, I guess. And look, here's that blue in a real world situation. On a guardrail. As you can see, it has some signs of chalking. Given that shadow on my left, on there, you can probably tell that pipe or guardrail might run east-west. So there's a good chance underneath that shadow there's some good colour retention there with that particular coating. The other thing that to pick up on is that this has been damaged through cleaning of graffiti. So, like all good asset maintenance, programs, you do have to be on to replenishing the coating if it does get damaged, because you will get some visual differences as well from touching up as well. And if you're removing coating, obviously the durability of that system will deplete. We get to the signal red after 1,500 hours. As you can see, that visual there shows the signal red is still looking pretty good with the fluoropolymer. Hardly any change at all, and the polyaspartic is just starting to chalk up a little bit there. The 3,000 hours, all four of those panels except the fluoropolymer. There's a little bit of change in the fluoropolymer. There's a bit of white starting to develop. But in general, the fluoropolymer is still looking very good after 3,000 hours. The monument, massive change with the polyaspartic and the fluoropolymer still looking good. And look, there can be some colour variation from coating system to coating system too. So those changes with the fluoropolymer and the polyurethane there, they could have been both those were starting points for that particular colour as well. You cannot match exactly sometimes from coating technology to exactly the same. Normally you'd reference as a commercial match. And 3,000 hours, you know, the Colorbond monument looks like Colorbond off-white in some instances there. And the fluoropolymer, there is some change there after 3,000 hours. So the conclusions of the QUVB testing, you know, like I say, evaluating the resin of the top coat also under harsh UV light. It doesn't replicate sunlight, but it's a higher level of UV which gets pushed. The coatings are really pushed to their limit, but it's good to be able to find out what they can do. The range of performance was pretty drastic, really. I would have liked to share some 4,000 hours. I didn't have those available, unfortunately. But out of all those three colours, the fluoropolymer was the greater performer across that test of the 3,000 hours visually, which we saw. The Q-Sun testing, it's a little bit different. So pretty much that whole panel there is tested. So it's only really the outside of that panel which you'll be able to visually see any colour change from. But as you can see, after 4,000 hours, the fluoropolymer hasn't really changed as much. Where you should look back at the polyaspartic and the polyurethanes, there is some change compared to the edges of those panels. Polysiloxane is still looking quite a good option in that blue there as well. But in the red, completely different story with these particular test panels of the red. They're all showing some signs of you know, colour loss or some sort of chalking. As well as the monument colour as well. All fairly similar, not too bad, better performing colour, you know, test there because they're all fairly similar, you know, in that result there. On the graph for the Homebush blue, so after the 4,000 hours on the vertical axis there, with the delta E, the fluoropolymers, you know, around 1.2, I think it is there, whereas the polyaspartic is way up the top. Its delta E's gone through the roof there. The fluoropolymer, it's over the 4,000 hours, hasn't really changed after about 300, 500 hours there. It's performed fairly well. The signal red, the fluoropolymer again is performing pretty well, but the delta E has risen there up to about 1.2. Again, you're getting some mixed results with the other coatings, so there's no real consistency as to, you know, first, second, third, fourth, you know, as the better coating system. And the monument, the fluoropolymer is pretty level all the way through. Funny enough, the siloxane provided not as good a test on that one, where visually it sort of didn't look too bad. So the conclusions on the Q-Sun, typically the fluoropolymer coating will outperform other technology types, but the colour plays an important role as drastic change is seen in blue and red, but less in the monument as well. Although I mentioned we tested 4 coatings, you're wondering why there's 5 panels up there. We put 2 polyurethanes in there, and they both performed differently. So it's really a case in point where, you know, equivalents aren't equivalent. A lot of the time we will see on architectural schedules or other, you know, specifications or approved equivalent. So Sometimes what might be said as an approved equivalent might not perform as an approved equivalent. And the result may be similar also if we provided 2 polysiloxanes in the test or 2 fluoropolymers as well. You might get some quite larger variation. It's just that for this test we chose 2 polyurethanes on that. And there you can see there's a big gap halfway through that test, but they sort of come back to a more level field at the very end of that 4,000 hours with the polyurethanes with that QSUN colour change test on there. How is colour achieved? So with pigments, of course, inorganic pigments or organic pigments. You'll probably find, like the monument colour, inorganic pigments are used a lot in those, or your whites and your soft hues, your inorganic pigments. As soon as you go to something bright, bold, clear, sharp coatings, you're starting to use some of the organic pigments there. And of course, we combine those pigments to achieve colours as well through inorganic and organic. So there's an example of the colour-bond colours there, inorganic, and a bright yellow with an organic. So the inorganics, they will show less colour change. The chart there just shows the difference there with the fluoropolymer. Just noticing the delta E is still very low there, the record, but after the 4,000 hours, the monument with the inorganic pigments, its colour stability is really, really good. As I mentioned before, that you do mix them both together, and this was the case with the blue, the pigments. So that blues do use a lot of white, which is an inorganic pigment. Hence, that's why you're seeing that reaction with the colour change, and it's almost, the white is almost attacking the blue pigment and taking over that colour. For long-term colour durability, Rob did touch on this a little bit, but the top coat technology choice makes the largest impact on colour durability. Along with, depending on the exposure of the environment that the coating system will be in, but there is the top coat technology will far outweigh, do a lot of the protection, as Rob mentioned, and with your intermediate barrier coatings and your primers doing a lot of the heavy lifting underneath as well. So I guess when you're specifying colours, a lot of you may not specify colours in this room, but formulating practices is a discussion which we're happy to have with clientele to provide the best outcome with colour choice. A little case history here. Those of you that are from Melbourne will probably see these when they're coming out of the airport into the city. The red sticks. So the left end was painted there in 2012. The 2006 version is what you can see is faded. In 2012, they made a manufactured or a milled colour in the red, as opposed to adding tinters manually to get that colour. And as you can see, after 5 years, there is that was a urethane, mind you, after 5 years, there is better colour stability in that coating system on that. There's another example. Might be a bit hard to pick up those, but organic pigments, full UV exposure. The 3 green colours are really sort of well, not green really anymore, but the organic yellow, has lost its durability there, and the inorganic pigments in some of those charcoals, the grey darker colours, are still holding fast with their colour appearance. And durability is important for maintaining aesthetics. I think we're all probably creatures of habits a little bit. When we're purchasing something personally or through a business, if something does look shabby, we're probably going to walk to the next thing that looks glossy or new. So keeping up aesthetics, especially for business, is a massive thing for them. On the left, the Gold Coast, and they're both in the Gold Coast, but they chose to use fluoropolymers there just to keep that colour durability and stability for a long, long time. Whereas over in Cairns, some inorganic pigments were used and chosen with their coating system, and again, that will provide them extremely good colour stability for a particular amount of time also. Infrastructure projects are difficult to reach, and that was something that Rob mentioned about, trying to paint around a suburb with rail infrastructure, very difficult. Recently we've been able to have fluoropolymers used just across the road here at Central Park, where they did the cladding refurbishment. At the same time, they decided to paint the steel spires that you see on the outside of the building and the rakers, and they chose to use the V92, or sorry, the fluoropolymer, because of to repaint something like that in 10 years, 15, 20 years is just going to be astronomically expensive and difficult and dangerous. So fluoropolymer on that particular job was chosen, as well as the Wacker framing lights just recently as well. Again, difficult to access. So to go with a coating system that provides good colour stability was chosen. If your colour is hanging in there, then it's protecting what's underneath, and that means you're going to get great corrosion protection. Conclusions. Well, I think the bottom line there is correct pigment choice and highly durable resins will give you maximum colour durability, and hopefully less maintenance and less costs as well. Although the Australian standards provide information on corrosion and a guide on corrosion and durability of those coating systems, there's no real information around colour stability. Hopefully, you've noticed in that presentation the fluoropolymers outperform other coatings for colour and gloss retention. It's a lab test, but it's a good guide as to what you can achieve when you're using fluoropolymers in those instances. That was it. Thank you for listening.